One of the problems we have is that working derivatives versus working integrals are very different. Get back here. It's an XKCD cartoon. I love XKCD. They're so completely on the universe of nerds. The left side is taking derivatives. Look, can I use the power rule, the chain rule, the product rule, the quotient rule? Can I try logarithmic derivatives or implicit derivatives? That's really it. The right side is integration. Parts, substitution. Does it work? Yeah, right. Okay. Partial fractions, Riemann. Okay, wait a minute. Everything past here, I don't know yet. What the hell is going on here? Derivatives are, in some sense, the much easier version of the game. Why we did them first. But now that I have all these different methods for doing integrals, how do I decide? What's the appropriate strategy? I will say that fortunately for us, in spite of the fact that there is no guaranteed technique that will always work for any given integral, we are in a position to get the majority of what we've got in front of us. And really, here on page 506, this is what I need at the moment. Now, some of this we don't have to remember. Some of this is on the formula sheet. So I will guarantee you, you need the first three. Page 50, I'm sorry, in this book, 503. Page 503. The first one's the power rule. Works for any power except -1. And here's what happens when you use -1. So these first two are the power rule. The integral of e to the x is e to the x. Change of base. And the chain rule, use substitution, gets me this one. But that's on the formula sheet. I don't need it. 5, 6, 7, 8, 9, 10, 11, 12. Those are all on the formula sheet. I don't need them. I don't need them in my head. They're in front of me. These two, tangent and cotangent. Well, we did one as homework and the other in class. You do tangent as sine over cosine and you use substitution. You do cotangent as cosine over sine and you use substitution. We didn't do hyperbolics. You can scratch these completely off. We didn't cover them. I'm not going to do them. That's a use substitution I mentioned at the end of class. That's inverse trig. That's partial fractions. And that's partial fractions with a trig substitution. So these are all doable with techniques we know. Out of this, I really think adding to my memorize list should be 17 and maybe 18. But that's a trig sub, so I really don't need to memorize it when I have the technique to do it. So I could simply start jamming my head full of different formulas and just keep trying one after the other. But what I really want is some sort of method of pattern recognition and some sort of better idea as to how to go about making things easier to work with. So let me start with what I think is the easiest first option. Right away, my first idea, can I make this easier to deal with? How would you attack this problem? Yeah.
I was thinking you're going to use u as, like I say, u is tangent. I mean, I said u is secant squared, and then du.
But the derivative of tangent is secant squared, right?
Yes, this is the top end of the word.
Right, that's my problem. This is on the bottom. I can't do it that way. But I like where you're going with that. If I could get tangent and secant squared in the right places. But I don't have them that way at the moment. Do it. Tangents and secants make me twitchy anyway. Unless I really see that UDU substitution, Leo, I'm going to try and do something else. And with secant squared being in the bottom of this, I don't know how to deal with that. So I'm not going to. Nope. Let's cheat. Turn on the sines and cosines. Let's see if that makes it nicer. We had the same, as a matter of fact, this exact problem in trig. If you took trig here, this is one of the exercises I assigned in the section on trig identities, where we started using all the relationships we knew to try and make things simpler. In this case, I figured, hey, let's try sines and cosines. What do I get? Say again?
Sine theta, cosine theta.
Walk me through getting there.
So it's sine.
Why am I happy to see that?
You do a u substitution, very easier.
Ta-da! U equals sine, D equals cosine theta, d theta. I'm done. This is much easier. That's not the only U substitution I could do. I could do other ones, right? Because this is also part of the double angle formula for sine. Sine of 2, this one's right? Sine of 2 theta is 2 sine theta cosine theta. So I could from here do several different options. But now that's easier. So there are options for me to play with at this point. And again, my reaction is, upon seeing this integral, bleh, that's disgusting. Forgot the dx. Got to write in the dx. So what can I do here? If I expand it out, what do I get? Yeah.
If you expand it out, then x squared plus 2 sine of x plus sine squared of x.
Give me that middle term again.
2 sine of x.
Oh, wait, no. 2 times the first times the second. I get 2x sine x. Be careful. Algebra mistakes will drive you nuts here, and they're easy to make. Now, again, my first reaction is, I'm not thrilled. But if I do these as 3 separate pieces, then I actually do know how to do each one. What do I do for the first one? Just what rule, Tom? Power rule. For the middle one.
Maybe integration by parts.
Exactly. Integration by parts, IBP. My most common shorthand for integration by parts. And using the other mnemonic memory trick, I know that the U should be X and the DU should be sine X. Because polynomial comes before trig, L-I-P-E-T. What about the last one? Say that again? I do the sine squared equals. You started mumbling, I lost what you were saying, or at least I'm deaf with the air. If I make it 1 minus cosine squared, I still have a cosine squared. My problem is the square. So I like where you're going, but I think that's the wrong formula to use out of the trig pile.
Which one do you like? 1/2 times 1 minus cosine of 2x.
This is where I use the double angle formula to get rid of the square. So sine squared of x is 1/2 1 minus, I wrote it down, otherwise I'd never remember whether it was minus or plus, cosine of 2x. So really that makes that last integral the integral of 1/2 minus the integral of 1/2 cosine 2x, and that's a U substitution. So please notice, to do what looked like one integral, I actually need 3 different tricks. I need to do the algebra to expand stuff out. I need to do parts. And then I need a double angle formula to do the trig with a U substitution in it. That's technically 4 tricks. Questions? But notice now I've gotten to algebra, and then all of a sudden, I need other things. Twice here I've said I can do a U substitution. I'm happy to see that. So really, I think that's actually my second layer is quote unquote easy U substitutions. I think this was a homework problem. I believe it was the one I graded from section 7 too. Which means, because it was in the trig subsection, most of you did the secant part. X squared minus 1, I should use x equals secant theta, and then I get this big ugly integral in trig. I can do this without any trig at all. But by putting it in the trig subsection, I primed you to do trig sub, so most of you did it that way. I don't have to. If I do a, quote, easy, unquote, u sub, what's this integral turn into?
Would be 1/2 times the integral of du over square root of u.
Which is u to the minus 1/2 du power rule. And not even a terribly nasty power rule at that. Last year, when my class saw this problem, they wanted to shoot me. Trig functions inside trig functions, how dare you? Until one of the students went, wait a minute. What do I have here? Hold on, Leo. What do I have here is a nice, direct sub. Leo?
You can say that u could be sine of x, and he could be cosine of x to the x.
Which makes this a trivial integral. And I'm basically done, because the trig formula sheet has the derivative of sine being cosine and the derivative of cosine being minus sine. I know exactly what this antiderivative should be. Now, I put the word easy in quotes here because what is obvious to one person is not obvious to the next person. And the only way by which you start to recognize a u substitution fast is by seeing the whole pattern. So I would love to tell you that there's a nice, easy way to get this pattern into your brain, but I still hear that little rattle of one nesting doll inside the other in the back of my head every time I look at an integral and see something in parentheses that isn't just an x. That's my key. Hey, I see that inside. Maybe I should do something to make that nicer. But that was the same thing I saw here. The square root of stuff, not just an x. Make it nicer. If I can. Questions? Do we recognize this? Is it a pattern I recognize? So, when I see trig functions, I'm going to look for two things. What are the two things I'm going to look for when I see trig functions? Did a whole section just on trig functions. What did it tell you to look for? My Pythagorean identities when I can use them. And I use those in conjunction with a u substitution, right? I did the Pythagorean identity to pull one odd power out. Now, why did I write those four down? Secant squared, secant tangent, cosecant squared, cosecant cotangent. Those are the du parts for a u sub. Secant squared is the derivative of tangent. Secant tangent is the derivative of secant. Minus cosecant squared is the derivative of cotangent, but I can fudge the minus sign. Cosecant cotangent, again with a minus sign, is the derivative of cosecant. I can fudge the minus sign. If I see these things, then those should be the du. And if I see what I think should be the du, then I know what should be the u, and then I can use the Pythagorean identities to make everything into that trig function. If I have cosecants and cotangents, I can use the Pythagorean theorem for cosecant and cotangent to turn everything else into the u once I know which part is du. And if I don't see the right pieces floating around, then I'm probably going to try and turn it all back into sines and cosines, which again is going to give me that Pythagorean identity. Or at the worst, isn't tight, maybe I'll need some of the double angle formulas. And once I have this one, this bottom one with the cosine 2 theta, I can use Pythagoras to get the square reducing formulas if I need those. So please understand, 99% of this comes down to a grand total of 3 trig identities that I need to have in my head. Pythagoras and those two. Everything else falls out of those. If I need it, I'll build it. I don't like carrying a whole bunch of formulas around with me and then, oh, I have 8,000 of them, but I really only ever use 6. So I really just have those couple and then I derive the rest as I need them. What if I see rational? Somebody remind me, what's a rational function again? Not Mr. Spock. Radicals are roots.
You mean like a fraction?
Rational, like a rational number, it's a fraction. So that's my p of x over q of x thingy. And then I'm going to hope for partial fractions. Because I've got a fraction, I'm going to try and do partial fractions. Maybe if I have to, I'm going to have to do division too. As we saw in some of the problems that were assigned from the work we did on Friday, I might need division, I might not. I don't know in advance. If I see a root, radical functions, well, that's what that symbol's called, right? A radical. If that stuff under there matches my squares patterns, then maybe I'll do a trig sub. If it's not a square root, say it's a cube root or a fourth root or something weird like that, well, then I'm probably going to have to do a different kind of substitution. Hopefully I'll have f prime on the outside and I'll be able to do a u substitution. Maybe I'll have to do u equals the whole thing. Because that's sometimes when I do the derivative of that, I get 1 over, right? Because you'll get, like if you have the cube root, that's a 1/3 power. So when you take its derivative, you get a negative 2/3 power. You put stuff in the bottom. All of a sudden, things start to work better. What if I have a combination? You know, a polynomial part and an exponential or a trig or a logarithm or something else. What should I do then? I even put the word in it, parts. I'm pretty sure I'm going to end up doing integration by parts here. Now here's where the rest of that cartoon comes into play. Because I could do one of these. I could do more than one of these, and I could be still stuck. Huh. At this point, the answer is try something absurd. Try something weird. Let's do a really funky substitution. Remember, we did one where we did u equals x minus 1, and then we also did x was u plus 1. We had to use the substitution more than once. So we could have a funky substitution. And here I will agree that lucky guesses help. And my answer is, well, how did you know to do that? Well, I tried everything else and I was just shooting darts at the board to see what would stick. And that, unfortunately, is more common than I would like, because I would really like very deterministic methods to nail all this down, and I don't necessarily get it. You could try parts anyway by letting dv just be the dx. And then maybe that makes your life easier. Because when you do v, you'll get an x floating out, right? Maybe that x is exactly what you need to do the integral of v du. Extra x on the outside now gives you a new way to do a substitution, gives you another option. These are two of my favorite tricks. I'm going to multiply by 1. But that 1 is going to look like, I don't know, the square root of e to the x over the square root of e to the x, so that I can do some other stuff. Or I'm going to add 0, which means I'm going to add 2 and subtract 2. Those balance each other out, right? I'll add an x and subtract an x. Then I'll be able to factor differently, maybe. So multiplying by 1 and adding 0 are algebraic tricks that actually help us a lot in doing integrations. We did this also in trig, where we did trig identities. I want to try and integrate this. And I'm going to say right up front that none of my trig formulas are going to help at this point. Because I don't know what to do with a 1 minus in the bottom. Leo?
You multiply by 1 plus cosine x or 1 plus cosine x.
This is called a conjugate expression. And the reason I use it is because now what happens when I multiply on the bottom, I have a minus b times a plus b. That's the factored version of the difference of two squares. Patty, now, Pythagoras. Now, Pythagoras comes, 1 minus cosine squared is sine squared. But now I can see some of you, but that doesn't make it any nicer. You're right. Written like this, it isn't any nicer. But I can split this into two pieces. 1 over sine squared and cosine over sine squared. Why am I happy to see that? Well, because 1 over sine squared is cosecant squared. And then I have 1 over sine squared times cosine x dx. Do these as two separate parts. The first one is on my formula sheet. That's negative cotangent of x. Second one is a u substitution. This sort of algebraic messing around is what leads to things like the formula we saw for doing the integral of secant of x, multiplied by secant x plus tangent x over secant x plus tangent x. Where the did they come up with that? Algebraic messing around to see if we can make our lives easier. Here's where my pattern matching statement comes to the forefront. Have I seen this garbage before? If I look at this problem and I get the real sense of deja vu, I'm going to go, wait a minute, I've seen something like this. I'm going to start looking back in my notes. I'm going to start looking back in my textbook. I'm going to start looking back and going, where did I see something like this? Where did I see a pattern like this before? Now, the downside to that is that the only way for me to have seen these patterns before is to do a bunch of these problems and to read a bunch of these problems. That means reading other people's solutions and doing my own so I can get those patterns into my own brain. This is the case where there is no good substitute for practice. I want to build, for lack of a better term, I want to build muscle memory. I want to build that instant pattern recognition. A very long time ago, in a galaxy very, very far away, Miami, I took karate as a kid. I cannot tell you the number of times I threw a front kick. Really easy. But I never quite got the technique down. And my instructor would say, no, you kick from your knee and your hip, not with your foot. You kick with your knee. What are you talking about? I'm going to hit you with my foot. I should kick you with my foot. Kicking you with that knee in somebody. What are you talking about? For like a month, he'd stop me, turn, stand behind me, hold my head, and kick with your knee, and he'd move me. And I did not understand. I did not understand until one afternoon I kicked with my knee. That's the only way to describe it. I suddenly knew what he meant. The pattern made sense. You turn here, you lift here. Your foot's going to get there, but move your body weight with your knee. You aim with your knee. You point with your knee. You hit, you kick with your knee. What? For a solid month, you told me kick with your knee. No clue. I guarantee you that at some point, you're going to look at a problem and go, power roll, I see it. Trig sub, U sub, parts. It jumps out at me. I see the form sitting in there. Only way to see that form, see it a lot in front of you, to do it a lot, and suddenly the recognition happens. I'd love to tell you that you can make flashcards out of these things. You could. You could make integral after integral after integral flashcard. And then it would simply be a matter of you turn it over and you tell me what technique to do, and it's written on the back. It'd be great. I'm sure somebody makes a set of those somewhere. We made them for the actuary exams. We can find them for this course. But that idea of pattern recognition only shows up after you see a lot of patterns. Oh, and last but by no means least, you may need more than one trick. Your U substitution may lead you to an integration by parts problem. Your multiplying by 1 may lead you to a U substitution problem. Your trig sub may result in a trig integral that needs the odd powers and the trig identities. So depending on what we do, we may need multiple tricks in this process. Here's an example of a weird trick. What would you really like to do here? Other than run screaming and throw the book at me. It's always an option, but it doesn't result in solved problems. I'd like to do a U sub. And if I were to do that, what would be your choice of U? Say again? Well, then if I do just U equals X, then the problem becomes e to the square root of U du, which is exactly the same problem. Aha! If I do U equals the square root of X, then what's du? How? Wait a minute. This is X to the 1/2, right? So when I do the derivative, I get 1/2 X to the negative 1/2 dx. I don't have any of that crap out there, do I? But another way to write this is to say that du is 1/2 1 over the square root of x dx, right? I still don't have that square root of x on the bottom on the outside, do I? I don't have it there. I'm going to multiply by 1. But the 1 I'm going to use is 2 square root x over 2 square root x. If I take the 2 and the root x that's on top, and I put the 2 out front, and the root x at the front, then I have 1 over 2 root x dx. And isn't that my du? 1 over 2 root x dx is du. Multiplied by 1. If you do the u substitution, what do you get? Which is integration by parts, isn't it? Son of a... I got to something I know how to do. We did this problem in class. I wrote it as x e to the x then, but we did this problem. I know how to do this. This is integration by parts. And that makes me happy. Now, when I was shown this trick, I wasn't shown it as multiplying by 1. So I'm going to show you the same trick. I'm just going to write it a little different. Instead of writing, maybe not. Instead of writing u equals root x, I'm going to write u squared is x. Now, normally we would take the derivative, right? And I'd have du dx. But what happens if I take the derivative on the left? What's the derivative of u squared? But wait, there's more. That's implicit derivatives, isn't it? Because u is a function of x. So when I do the derivative of u squared, I get 2u, but then the derivative of the inside, du dx. I put that on the other side, and I get 2u du equals dx. Integral e to the root x dx becomes the integral of e to the u 2u du. Take the 2 out front, put the u in front. It's the same problem, isn't it? Now, the reason I didn't show you that version first is because a lot of people hate this idea. And in some textbooks, they'll show you this trick and then they'll say, so du is 1 over 2u, and they mix the du and the u with the dx in weird places, and I didn't want to do that to you. But that trick of doing the chain rule, of doing implicit derivatives in there, can work in more general situations. I think this is problem 32. That looks disgusting. It really does. I don't like it at all. What the hell am I going to do with a square root and a fraction in the process? Really, I'm going to need more than one trick. So, what trick should I try first? I gave them to you in what I consider to be order of difficulty. Can I do algebra trig? It's pretty straightforward. Can I do an easy use substitution? Then parts, partial fractions, trig sub, trig. Those are harder. I actually think partial fractions only applies if I have a rational. That square root prevents this. I can throw partial fractions right out the window. Not going to use it here. So what do you think I should try first? Well, what one would you multiply by? Not a problem multiplying by one, but do you see something that's going to make it nice if I multiply by one? Okay, that's my problem with the multiply by one idea. I got to see something that's going to make my life easier. And I only figured out what one to multiply by after I kind of looked at a use substitution, right? So let's play with a substitution. If I were going to try and do use sub here, what do you think I should do for a use sub? Rattle, 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 rattle. We'll go with the stuff with the square root, right? Huh. Okay. Then that top is now u under a square root, yes? What's the bottom? Aha! What's du? There's more. Exactly. I don't have the 2, so I'll get a 1/2 floating around. Wait, just a second here. I see a pattern in my head that we're really close to. It would be nicer if on the bottom here, instead of having u, I had u squared plus 4. Page 503, that table on page 503 had x squared plus a squared on the bottom, or u squared plus a squared. That would be a trig sub. So what if I didn't have a u on the bottom, but I had a u squared? Oh, I forgot to write the du here, sorry. You with me so far? Why is this better? Oh, because now that's a v squared plus 4. What's dv? Leo? 1 over 2 root u du. This is that same multiply by 1. I'll multiply by 2 root u over 2 root u. I've seen this before. Now all of a sudden I have a path to proceed. This is going to actually result in a rational function, which means after doing these substitutions, I get to do partial fractions. Partial fractions actually work out to be really freaking easy. So, in spite of the fact that it took me a while to figure out what I actually wanted to use for the right substitution, I think I end up with some place I can proceed well from. Warning. Not all integrals can be done. That problem has no antiderivative that I can write in a nice form in terms of other functions we've already seen. That's called a closed form. This has no closed form. So in spite of me being able to do lots of different techniques so far, even if I add in all the other techniques in the world, I will still end up with problems I can't do, that no one can do. So what do we do with those? We'll find out on Wednesday. I have summarized all of this idea into a sheet that is on our Canvas page. You should take this, print it out, and use it at the moment to keep going through what our pieces are.